Okay guys, I'm going to make a couple videos for the math on this just so I can kind of keep everything together. This one's going to be just about lenses, the diagrams, and also how to find the um, actual lengths using mathematics and the equations. So let's go ahead and start with kind of how the lens laws work. The ray diagrams for a converging lens, right? This is a convex converging lens. So let's see here. So we know from your notes that the first ray you want to pick a common point each time. So I'm going to go ahead and pick the tip, the top, tippity top of this right here. And I'm going to go, this is the exact same walls, by the way, as the mirrors, except now these have the ability to go through. Okay, these have the ability to go through. So the mirror blocked it, made it bounce backwards, right? But this guy is going to go parallel to the principal axis, hit the center of the lens, and then it's going to try and go to the focal point. It's going to try to go to the focal point just like that. Okay. And now the second one is going to start also at the tip top. I'm going to go ahead and make that a different color. Let's go ahead and make it blue. This guy's also going to go here. But instead of going, it's going to do the opposite of the first ray. It's going to go straight through this focal point on the same side. And as soon as it hits the mirror, look what it's going to do. It's going to switch and do parallel. It's going to go parallel to the principal axis. And guess what? Where these 2 points meet is where your image is going to form. Where these 2 points meet is where the image forms. I'll go ahead and do that with red. Okay. And so what type of image do you end up getting? Well, if the object was upright, the image is going to be inverted. Okay, it's inverted and the magnification is negative. The magnification is negative. So this is one of the behaviors of what happens when our object is outside of the focal length. So this right here is the focal length. This is outside the focal length. Okay, so let's go ahead and look down further here. Now let's look at what happens when it's inside the focal length. Okay, so first law is what? Parallel to the principal axis until it hits the center of the lens. And then what's it do? Well, that's not parallel at all. Okay. And then once it hits there, it's going to try to go through the focal point on the opposite side. All right. Now this guy, since it's in front of the focal points within the focal length, we're going to have to do some kind of creative things here. Okay, so same thing. Instead of going backwards like that, you're going to go forward through the tip top. Right, it has to still hit the tip until it hits the center of the lens, and then it's going to switch and go parallel. Okay, now watch this. Since your eye believes that light only travels in what type of line? Straight lines, right? Your eye believes and your brain makes believe that the light travels in straight lines. Guess what? I'm going to go ahead and extend this back this way. Okay, it came from a source somewhere over here. Same thing right here. If this guy thinks that this came from here, look what's going to happen. Keep the same angle. And there we go. And so now where these two guys intersect, my image forms. And look what ends up happening. I end up with an image that is upright and magnified positively, bigger. Now, what something is worth noting here is that unlike the previous diagrams you had to learn with mirrors, this is the law of reflection for flat mirrors, right? All of the images were in a space, so if this was my object, my image, y prime, would have been behind the mirror. This was virtual space. You could not reach into the space, right? So because they were on the opposite side of the plane, they were virtual, right? But in this case, this guy here is able, the light is able to transmit through the lens and project onto like a screen. Okay, so if it's able to go from one side to the opposite side of the lens, that means the light from here was able to be projected and focused somewhere else. Okay, so this actually is a real image. Okay, so this is real because they're on the opposite sides. Opposite sides. Now look down here. This is what you would do with something like a magnifying glass, where you have the focal point, you know the focal point of the magnifying glass, and you put an object closer than the focal length, right? Closer within the focal length, and look what you would end up getting. what do objects look like they appear to do when you put them in a magnifying glass? Don't they appear to get bigger? Well, I showed you what happened when you get something like your hand, right? Or let's say, let's see here. So if I put like a little smiley face down like that, I can do two things, right? I can either really draw a larger smiley face, or I can just bring the smiley face closer to you, and what's it going to do? It's going to look like it got bigger, right? So when you get a magnifying glass and you put something within the focal length, it appears to get bigger, which your brain tells you is the same as bringing it closer to you, right? So if your face is right here, right? And you're putting this object in front of a magnifying glass, if you're putting this object in front of a magnifying glass, what's this magnifying glass, or what's your brain going to tell you it's doing? It's going to tell you that this guy is actually getting bigger, right? And so that's an illusion. And since these are on the exact same side, the object and the image are on the same side, this is not really happening. You cannot project this image onto a screen. It is an illusion that your brain is doing. Okay, so this is actually virtual. Okay? So when the object and image are on the same side for lenses, it is virtual. Okay, and that's important because it's going to bring us to our diverging lens, concave lenses. Okay, so let's look at what these guys do. I'm going to do a couple examples real quick. Okay, so the walls are the exact same, right? You're going to go to the center going parallel, but since these diverge, right, you have some pictures of these diverging light. We need to know the focal point determines the angle at which they'll diverge. Okay, so it's going to bend. We don't really know, like, what's the angle that this guy's going to bend. Is it up here? Is it up here? I don't know, right? So I'm going to use the angle of the focal point on each side to help me determine the angle at which it's going to bend upwards. So you see that, how it kind of meets the center guy right here, and then it's going to continue to diverge that way. So notice I kept the angle the same, right? So it diverged up like that. Okay, now the second ray is going to go, it's going to make a mad dash straight for this guy over here. Okay, so you see how it's trying to hit this focal point here? But once it hits the center, it's going to continue its path straight this way. Okay, it goes parallel, just like all of our mirror walls, just like all of our lens walls. The first one starts parallel, and then it follows the focal point this way. The second one goes follow the focal point, and then it goes parallel to the principal axis, right? Really easy. Now I need to have some sort of intersection, and since my eye believes that light only travels in straight lines, I take this one and go backwards, right? Just like that. And look what ends up happening. I get an intersection in front of the lens, the same side my object is at. And actually this is true all the time for concave diverging lenses. You always end up with an upright relative to the object, and you end up with a negative magnification. And in the next video, I'm going to go over how to actually calculate these two things. All right, good luck on that. Bye.